Hello and welcome to today's session. We're looking at satellite motion, and there's two objectives for today's session. So the condition needed for satellites to be in stable orbit, and to describe what happens to the speed of a satellite if it moves closer to the Earth. So for this, we need to think about Newton's law of gravitation and relating that to the centripetal force. So we'll look at how Newton's law of gravitation was used to prove Kepler's third law for planetary motion. So Kepler's third law was found by looking at the orbital time of the planets and comparing that to the orbital radius. So planets orbiting the sun. So t squared is proportional to r cubed, where t is the time period of orbit, r is the mean radius of the orbit. Newton was able to prove this. So Newton's law of attraction, gravitational attraction, if you recall, F was equal to gmm over r squared. So if we're going to think about that in terms of planets orbiting the sun, capital M would be the mass of the sun, little m would be the mass of the planet, r is the distance between the planet and the sun, so the orbit radius. That is shown to be equal to the centripetal force. So you can imagine we've got this gravitational pull due to the attraction between the mass of the sun and the mass of the planet. We can equate that to the centripetal force, so linking topics together. As I said, capital M, mass of the sun, m, mass of the planet, little m is the mass of the planet, and v is the speed of the planet in its orbit. So we can equate the two. We'll look at the acceleration. So if you recall, the centripetal acceleration A was equal to v squared over r. And we can think about that, how that relates to the gravitational field strength. So recall the gravitational field strength can be expressed in terms of an acceleration. So we'll use that in the satellite motion questions that will come up in the topic. So the gravitational field strength can be expressed as an acceleration. So acceleration or as the force per unit mass. If you look at the equation for Newton's law of attraction, G, the field strength, can be expressed as gm over r squared. And centripetal acceleration from circular motion equations is equal to v squared over r. So we can equate the two to get an expression for v squared. So if we equate the two, v squared over r is equal to gm over r squared. We need to have v squared, so an expression for v squared, so that we can use another assumption for circular motion to get to Newton's proof of Kepler's third law. So make v squared the subject, v squared is equal to gm over r. Assuming that the planets are orbiting the sun in a circular orbit, we can find the speed, because the speed is equal to the distance traveled, so a circle divided by the time period. So assuming it's a circular orbit, with the circumference divided by the time. Okay, so we need to get to the proof of Newton's law with the Kepler's third law. So we need an expression with r cubed and t squared. So t being the time period. If we know that the velocity or the speed of orbit is 2 pi r over t, because it's in a circular orbit, and previously we've said that v squared is equal to gm over r, we can equate the two. So we can square that expression for v and have an expression for v squared. So v squared, 2 pi r squared over t squared, where t is a time period. Now all we need to do is bring the r's on one side and move the 2 pi onto the other side. So if we square that, then what do we get? So if we put that next to this, we get a 4 pi, let me put it over here, 4 pi squared over r squared t squared is equal to gm over r. So all we need to do now then, bring the r's to one side and move the 4 pi squared over to the other side. So if we do that, we get r cubed over t squared is equal to gm over 4 pi squared. So Kepler's third law was that r cubed is proportional to t squared. So it follows that r cubed over t squared is a constant for all planets, and that's equal to gm over 4 pi squared. So that's all Newton did to prove Kepler's third law. So that's the proof, and we can use this relationship for satellite motion. So if you think about a satellite motion, satellites, you've got a satellite orbiting another body. So a planet, you've got a planet and then a satellite which is orbiting the planet. We can use this expression to work out the height above the planet that the satellite needs to be at. Thinking about this as well with Newton's proof of Kepler's third law, and that we've used the centripetal force. If you think about what happens to the separation, if we reduce the separation between the planet and the satellite, v increases. So if you think about the equation F equals mv squared over r, if we think about a planet here, and then we've got our satellite distance r away from the center, as r decreases, the value of v has to increase. So as we get closer and closer to the planet, the orbital speed increases. So that's what we can think about in terms of these satellites. And what we'll do is we'll work out the value for the orbital height for a satellite above the Earth. So we're going to calculate that as well. So an application for satellite motion and using the expression that we've shown in the past slide, r cubed over t squared is equal to gm over 4 pi squared, we can think about geostationary satellites. So geostationary satellites are directly above the Earth's equator, and they have the same orbital time period as the Earth. So it's 24 hours, and they remain in a fixed position. So we can use those satellites for communication. So TV, that type of thing, communication across the Earth. So if you have your skybox, that's what's happening. The actual dish on your house is being pointed towards the satellite. And if we had 3 geostationary satellites, if we put them in orbit 120 degrees apart, we can cover the entire Earth apart from right near to the poles. So that's the idea of having these geostationary satellites. We can use it for GPS as well. So with GPS, we can apply this. So we can track. Another example would be for tracking vehicles. So tracking vehicles as they move. The other thing with that is, because we have to put them so high, so we're going to calculate the height of a geostationary satellite. There is a high energy cost. So if you think about what we talked about in the previous lessons of gravitational potential, so the work done per unit mass to move a particular object from one potential to another. So moving from infinity to a point was our definition. But there's quite a lot of energy that's required if you need to move it to this position. We'll calculate that in a moment. So we can work out the radius of geostationary orbit, and that's what we're going to do next. Okay, so now we will calculate the radius of the geostationary orbit for the Earth. So this is a separation between the satellite and the Earth, between the centers of them. Once we've got that value, we can find out how high above the Earth the satellite has to be by subtracting that distance, the radius of the Earth, from the separation. So remember, the separation is between the center of the Earth and the satellite. If we subtract the radius of the Earth from that, we can get the height above the Earth. So if I sketch a little diagram of that, that's what we'll have. So in the top left, if we have a circle for the Earth, the satellite will be here, radius of the Earth, and then we've got this distance, this height above the Earth here. So change in height there. So making r the subject here in this equation will give us the total distance, because it's the orbital radius. So that will give us the total distance from here to here, because r is the separation between the centers of the masses. So in order to do this, we need to find the time period. Because it's geostationary, geostationary takes 24 hours to complete an orbit, same time period as the Earth. We need the time period in seconds, so t, 24 hours times 60 minutes times 60, again for the seconds, gives us 86,400 seconds. So that's the time period. We need to find r, so we need to make r the subject of this equation. So first of all, we'll have r cubed. If we have r cubed on its own, that's equal to gm times t squared, because we have to multiply both sides by t squared over 4 pi squared. Then we need to do the cube root, because it's r cubed, to find the value for r. So cube root both sides. We'll have the cube root of this. So the mass of Earth's given to you, the gravitational constant's given to you because it's on your formula sheet. So that's at the top of this question here. Now all we need to do is substitute the values into the equation, and we will get an answer. Remember, the time period is squared, so we need to square this value. And this is all over 4 pi squared. So, put that into your calculator. Remember to cube root the value, because it's r cubed and we need to do the cube root. Cube root the value, you'll get an answer of 4.2 times 10 to the 7 meters. So that is the radius of the orbit. So the total distance, the total separation between the center of the Earth and the center of the object. In this case, it would be the satellite. So if we want to find the height above the Earth that this is at, the height will be equal to 4.2 times 10 to the 7 minus the radius of the Earth. So radius of the Earth, RE, so we'll put it up at the top here, the radius of the Earth is 6,400 kilometers. So height above the Earth was 4.2 times 10 to the 7 minus 6,400. Remember, that's going to be multiplied by 10 to the 3 to have that all in meters. Gives us a value of 36,000 kilometers. We can find the kinetic energy of an orbiting satellite, and we can also find the potential energy as well. The total energy in the system will be equal to the kinetic energy plus the potential energy. First of all, the kinetic energy. Assuming the satellite moves in a circular orbit, we know that we can find kinetic energy as half mv squared. And earlier on in the session that we've looked at, we had an expression for v squared when we looked at Newton's law of gravitation. So v squared was equal to gm over r. We can substitute that into the kinetic energy equation and get an expression for kinetic energy. So gmm over 2r. Remember, capital M is the mass of the planet, and the lowercase m is the mass of the satellite. So total energy, as I said, will be equal to the potential energy plus the kinetic energy, and that is where the distance is r. Remember, r is the separation between the satellite and the planet. So if we want the total energy of the system, we need to find the potential energy. So we've got an expression for kinetic energy, but potential energy. To get the potential energy, we need to use the gravitational potential. So remember, the gravitational potential is the work done per unit mass. So to find the potential energy, it will be the gravitational potential times the mass. Gravitational potential minus gm over r. To find the potential energy, so if we think about the satellite, we need to multiply that by the mass of the satellite, and that will give us the potential energy. So minus gm m over r. So the total energy would be to add the potential plus the kinetic. So if we add those two together, that gives us the total energy of the system. If we need to add them together, they both need to have the same denominator, so they both need to be over 2R. Adding those two together gives us the total energy as Gm minus Gm over 2R. So in the previous section in the class, we looked at sketching graphs of potential. So we sketched a graph of gravitational potential for that -1/r relationship. We also need to be able to sketch a graph of kinetic energy and the total energy. So the graph would look something like this. So you've got in blue the kinetic energy, red the gravitational potential, and green is the total energy. So this could be one of your multiple choice questions where you need to select the correct form of energy. So you could have a graph and you'd have to select what does the line represent. So is it showing kinetic energy, is it showing potential energy, or is it showing the total energy of the system? That's a common question that will come up. So common multiple choice question for that one there. Or you might be asked to sketch potential. So sketch it. It could be a 2-mark question. Okay, so we'll look at this, which is a typical exam question that you can get around satellite motion. The first part then says to use the symbols to give an equation that relates the gravitational force on the satellite to the centripetal force. So you've got a satellite of mass m, travels at angular speed omega in a circular orbit at a height h above the surface of the planet of mass m and radius r. So we need to give an equation that relates the symbols. It might be helpful to sketch a little diagram to show what's going on. So if we have a diagram here, r is the radius of the planet, and then the satellite is a distance h above, and it's got a mass of lowercase m. This planet has big M, and it's got an angular speed of omega. So as it goes around, as it orbits the planet. Okay, so what we need to do is think about the start of this session. So the start of the session, we said you can equate the centripetal force to Newton's law of gravitation. So the gravitational force can be equated to the centripetal force. This is sort of a recap back to circular motion. So you can express circular motion as F equals mv squared over r, but in this question it talks about this angular speed. So in this case you're going to express it as m omega squared r. So recall we can express that force as m omega squared r. Okay, so what we need to do then to equate the two, we're going to use that, and we're going to use G equals m over r squared. So next line is just to equate the two. So if we put our gravitational force on the left hand side, G for the mass of the planet, m mass of the satellite, the distance, remember r is a separation between the two, so it's going to be r plus h, capital R plus h, because it's a separation. That's going to be squared equal to m omega squared. R again in this is r plus h. So r plus h. That's our expression. So that's the first part. We've got an expression for the gravitational force and the centripetal force. The second part, we need to find, or we need to show actually, we need to show that the equation from part B1, we need to show that it can be expressed for the time period. So we need an expression in terms of the time period. So if we look at this, there's no time period in there at the moment, but if you recall, omega is equal to 2 over the time period, 2 pi over the time period. So omega is equal to 2 pi over the time period, or remember it being 2 pi f. So remember the relationship between time period and frequency. Frequency is 1 over the time period. So that's what we need to use for part 2. We need to substitute into our equation. We need to sub in 2 pi over t. So 2 pi over t, where t is the time period. So part 2, gm m over r plus h squared m omega squared. So omega is 2 pi over t. So 2 pi over t squared r plus h. So we can see for the first bit, we can cancel out m, lowercase m, which is the mass of the satellite. So those will cancel out. Then, what can we do? Then, if we square that 2 pi over t, our next step would be this, wouldn't it? So we'd have for gm over r plus h squared is equal to 4 pi squared over t squared r plus h. Then the final step is the rearrangement for t squared. So bringing t squared across, let me separate this. I'll do it on the other side here. Let's do it over here. Next step, we need to bring t squared over to the left-hand side. So multiply throughout by t squared. And if we multiply by r plus h squared, we just change that. So t squared over here, gm is equal to 4 pi r plus h cubed, because if we bring that r plus h squared over to the other side, we get r plus h cubed, and then all we need to do is divide throughout by gm. So we get 4 pi squared r plus h cubed over gm. Okay, so that's what we need to do to prove that.